Hello, students. Good morning. Today I am going to discuss cryogenic engineering. That means I'm going to introduce cryogenic engineering. So here I am going to discuss what is cryogenics or cryogenic engineering, some of its flavor, some very important applications, and the starting of liquefaction process. So let us see what is cryogenic. Cryogenic engineering is actually deals with very low temperature. That is processes involving very low temperature. Now, very low temperature is a qualitative term. So it should have some quantification. So there initially this particular subject was developed in United Kingdom and afterwards USA, European countries, and so on. And at that time, at that point of time, that low temperature, that demarcation, that from which cryogenics will start, that was decided in this way. That means temperature up to which normal refrigeration ends. From there, cryogenic realm starts. So normal refrigeration means the temperature we can attain by normal using normal refrigerant. So now there was a concept during that time. Now also it is there that permanent gases. Permanent gases materials has three states of aggregations, and that three states of aggregation, solid, liquid, and gas, that we generally refer with respect to normal ambient temperature. So with respect to that temperature around this 20 to 30 degrees Celsius, in that range, materials which are present in solid forms, we call them solid, which are present in liquid form, we call them liquid, which are present in gaseous form, we call them gas. Now, these gases, of course, there are some gases, say carbon dioxide, ammonia. These gases, if we increase pressure, they will be converted to liquid. So that's why we did, we introduced the term permanent gases and gases which are not permanent. So on that basis, some of the gases which cannot be liquefied even after increasing pressure. Say, for example, oxygen, nitrogen, hydrogen, helium, etc. So these are the gases which cannot be converted to liquid form by increasing the pressure alone. That's why these gases are known as permanent gases. So most of these permanent gases boiling point is below 150, minus 150 degrees Celsius. That's why, based on this demarcation, cryogenic engineering or realm of cryogenics was defined. So, cryogenic engineering involved the design and development of systems and components which produce, maintain, or utilize low temperatures. As per National Bureau of Standards, US, it is engineering involving temperature below minus 150 degrees Celsius. So this demarcation was given at that time. This is a logical dividing line because the normal boiling points of so-called permanent gases lie below minus 150 degrees Celsius, while conventional refrigerants all boils at temperature above. So in that way, it was defined. Now, of course, it realms is increased because of the various reasons, lot of applications, new applications of low temperature science um, uh, are there. And so that's why even nowadays, minus 29 degrees Celsius also coming under cryogenic engineering. The reason is human cells are severely damaged by sudden contact with substances below this temperature. So with respect to that particular cell, so that some additional precautionary measures that we should take. So that's why this temperature, though this temperature was under normal refrigeration regime earlier, now it is also within this cryogenic regime. So this temperature represents the demarcation of embrittlement of carbon steel also. So there are a lot of changes, properties changes of materials. So that's why it is, I think, very important incorporation of including this temperature also under cryogenic regime because of lot of important applications coming out right now. So now let me give some idea about uh, the temperature concepts. That means uh, by which you will be able to uh, set the temperature level. So this thermometer is scaled on logarithmic scale. So you can see that it is that 10 power scale. So from here to here multiplied by 10, then multiplied by 10 to the power 2, 10 to the power 3, and so on. So this temperature, though absolute zero temperature, we have not able to attain. We have attained this temperature. So this from this temperature, this is about 0.05 to 0.7 or like that. This particular regime is under dilution refrigeration. So by using dilution refrigerator, we can attain this very, very low temperature. So, and above this 0.1 to up to 0.9 or 0.8 K magnetic refrigerator. So by using magnetic refrigeration, adiabatic um, magnetization, demagnetization process, we could attain this temperature. These are very, very low temperature. Now, this is the temperature of liquid helium. Liquid helium temperature is about 4 Kelvin. So And this is the temperature, liquid helium temperature. Liquid helium temperature is about 20 Kelvin. Liquid air 87 K, something like that. So this is 150 Celsius. So earlier, this is the starting of cryogenic temperature. So below this, that means up to this range, we used to call the realm of cryogenic, but now it is increased up to this level, minus 29 degrees Celsius. So about 303 K. So this is the temperature water freezes. So 0 degrees Celsius or 273 Kelvin. And this is the temperature, human body temperature. Uh, and this is the temperature at which water boils. Uh, so 100 degrees Celsius, so 373 K and so on. This is the temperature iron melts, and this is about 6,500 uh, uh, Kelvin is the surface temperature of sun, and so on. So this is to give some idea about the temperature range. So now I'm going to give you some flavor about magical phenomenon of cryogenics. Those are beyond our imagination. So we cannot imagine some of the properties. So while we are not able to imagine their cryogenic engineering or cryogenic science, uh, those phenomenon have given us hope for some paths uh, to imagine, to break the barrier of uh, conventional registrations and so on. So, superconductivity is one of such phenomenon. Actually, if we flow current through conductor, it will be facing some resistances. And what we call as resistance of that conductor, and due to the resistance, heat is generated. But some of the conductor composite materials at cryogenic temperature loses its resistivity. Means if we pass electricity through it, it will won't be facing any resistance at all. That means uh, 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 current flow will be enormous, infinity. So superconductivity that we couldn't imagine earlier. Now that particular things we have seen in cryogenics. Then superfluidity. Fluidity that means fluidity that means the flow properties. Flow properties is dependent on viscosity. So that means when we will be trying to flow fluid through pipelines, it will be facing some sorts of resistances due to viscosity. Um, So, at cryogenic temperature, say superfluid helium, we have seen that it is having almost zero viscosity. That means all the viscosity, viscous property will disappear and it will become superfluid. And with the help by utilizing these properties, now a lot of new inventions, a lot of new instrumentation, sensors have been developed, and those are working miraculously at that particular environment. Now, supermagnetohydrodynamics, that is also another important phenomenon by which all of you know that super colloidal, that colloid to that do the experimentations of that particular very important things and that was actually tested and that was successfully done, that all of you know. Now, another important thing is transonic and hypersonic aircraft. Uh, that nowadays superpower countries are uh, exploring this, and they already explored, and lots more are coming. That due to this cryogenic properties of uh, this hydrogen and some other components. They are uh, having actually what we generally think that they will be having less conductivity. But hydrogen, helium at liquid conditions, they are having more conductivity. So by using these particular properties, conductivities of hydrogen, they are being used as fuel, high solid liquid mixtures. And we now are able to use enormous thrust and utilizing that thrust, we could develop transonic and hypersonic aircraft. Even now, the missiles are also there. Then mirror fusions, and this is of course very very important. And this is not totally developed. It is under developing stage. Uh, that means we will be able to means explore enormous green energy if this is successful. So mirror fusions, that is that particular things are going on. And one more, of course, there are lots more, not one more. Josephson junction and squids. These particularly has replaced even and that chemical cells as standard. So we'll be able to use Josephson junction diode as replacement of standard cell for measuring voltage and utilizing the interference between electrical and magnetic fields in SQUID, that is superconducting quantum interference devices. We have developed lot of things. Most of the new instrument stations, computations, electronics are based on this. So now some important applications of cryogenics. One is space research. All of you know that cryogenic rocket engine, infrared astronomy, uh, so a lot more are there and will come in space research. Then this is of course not very new. Air separation and purification means with the start of cryogenics, these particular applications was there for productions of liquid oxygen, gaseous oxygen, liquid nitrogen, gaseous nitrogen, argon, and for various lot of applications, that steel making, then wastewater treatment, the medical applications, inerting nitrogen, application of nitrogen, creating inert atmosphere. And of course, they are used as various, raw materials for various process industries. Then production of liquid hydrogen for rocket engine and various other uses. Now, this is coming up like anything, that applications of hydrogen, and this is going to replace a lot of other conventional fuels. Then productions of liquid helium for supermagnet and various other uses. Of course, here you should know that liquid helium is there uh, uh, for that super magnetic applications. There, liquid nitrogen is also used. That means to maintain very low temperature, liquid nitrogen is also used for some applications where materials will be behaving superconductively at even liquid nitrogen. So that superconductors, of course, we call them high temperature superconductor. High temperature superconductor, also room temperature superconductor. Those are not a developmental stage, not even materialized commercially. So one more application is LNG, liquefied natural gas, and green energy. This is very important area for cryogenic applications of cryogenic is there. Then cryobiology for medical applications, a lot of medical applications of cryogenics is there. Then food technology, food preservations, transportations, etc. Processings also. A lot of applications of cryogenics is there in food technology. Then electronics and computer sciences, as I already mentioned, for utilizing of Josephson junctions and other microelectronic suites. A lot of developmental works are going on. So these are some of the favors that I want to give. So as chemical engineers, you have scope in this particular area, air separation and purification, production of liquid hydrogen, production of liquid helium, LNG. Of course, these are the common areas. So there also you can uh, contribute. So now this superconductivity, this I want to mention that when this is normal conductor, that means through that conductor, this field, magnetic field, will be able to penetrate. But when this conductor will become superconductor, that means it will become um, uh, completely diamagnetic. So it will be repelling magnetic field. So the resistance will become almost zero. Uh, one more important phenomena that I want to mention is the two isotopes of hydrogen. One is orthohydrogen and another one is parahydrogen. So orthohydrogen nuclear spin is in same direction. In parahydrogen, it is in opposite direction. So parahydrogen form is the stable form of hydrogen when liquefied. And ortho form is the unstable form, but this is in a normal state. So when hydrogen is in gaseous form, most of the hydrogen is in ortho form. 75% more than that even. But if we liquefy hydrogen, why I am mentioning this particular phenomena? Because initially this was phased, where hydrogen was liquefied and it was kept in a insulated container. And suddenly, after some time, what we found, observed that nothing was there. That means all the liquid hydrogen evaporated. And after investigation, it was revealed that it was happened due to this conversion, ortho-hydrogen converted to para-hydrogen, and this is exothermic process. So when ortho-hydrogen will be converted to para-hydrogen, lot of heat will be generated, and those heats are sufficient to convert liquid hydrogen to para form. So nowadays, before liquefaction, ortho-hydrogen is converted to para-hydrogen catalytically so that it will remain in liquid form for longer times. This particular phenomenon is observed in liquid helium. So liquid helium boiling point, as I mentioned, normal helium is at 4K. But if we reduce the temperature by evaporative effect, then gradually this temperature could be reduced to that level. Suddenly, when the temperature of the helium will be attaining this temperature, about 2 Kelvin, what we observe that specific heat actually gradually decreases. Suddenly at this temperature it will increase and it will, after that of course again it will fail. So at this particular temperature it will become almost infinity. So sudden this curve is just like lambda. So this particular point is lambda point. So this is because at this point this uh, normal helium become superfluid helium. So it also become superconductor. Superconductor for heat, so that means suddenly, at this temperature, it was boiling. Suddenly, it will become very calm, and only we'll see surface evaporation. So this is very peculiar phenomenon that we observe in case of liquid helium. Very interesting facts. Now, uh, how we can produce coal, production of coal, and by this particular means, we will be able to uh, liquefaction because until and unless we produce coal, we won't be able to convert gas to liquids. So there are two important thermodynamic phenomena by which we can produce coal. One is Joule-Thomson effect, and another one is expansion valve. So one is uh, adiabatic expansion, and another one is isentropic expansion. So by this uh, two process, we can produce coal. So this Joule-Thomson effects, this is uh, uh, observed for most of the real gases. That means when real gases are suddenly exposed or suddenly uh, flown through some small apertures from high pressure to low pressure, some suddenly temperature falls, and this is falling due to internal work done by the gas, and this is happening when we do this below inversion temperature. So That means this is giving us some clue when we will be getting cold, when we won't be getting cold. So most of these real gases, inversion temperature is above ambient temperature or near about ambient temperatures. That's why for most of the real gases, Joule-Thomson effect is applicable. But for other gases, say permanent gases, uh, say for example, hydrogen and helium, for them inversion temperature is very, very low. So there we cannot achieve cold at all by 2000 effect. So their only option we will be having, that is isentropic expansion. So the change in temperature resulting from a substance expanding from one constant pressure to another constant pressure with the heat transfer and no external work other than to maintain constant pressure. Inversion temperature, the maximum inversion temperature for a van der Waals gas is the temperature on the inversion curve at P equals to 0. And this can be divided into two groups. That is when maximum temperature is greater than room temperature, and for those when the inversion temperature is below the room temperature. Expansion valve and adjustable orifice through which Joule-Thomson expansion occurs. Expansion engines, a machine to extract heat or energy from a gas by causing the gas to flow through a piston or turbine wheel as it expands between two pressure levels. As the energy is removed, the temperature of the gas decreases. So by these two processes, we can attain cold. So here this particular inversion curve has been shown. So these are the range where Joule-Thomson effects are there, and these are the range where that is reverse of Joule-Thomson. That means even we expand the gas, there will be some increase in temperature. So here that isentropic expansion and isenthalpic expansion. So these are the cars, say AB. AB is isentropic expansion, and AC is uh, isenthalpic expansion. So you can see that due to these two processes, maximum cold will be able to attain in case of isentropic expansion. But in case of isenthalpic expansion, temperature drop is not that much. So always we'll prefer by expansion engine, but there is some disadvantage of using expansion engines also. That's why expansion valve or jetty valve is so popular, because expansion engine cannot work uh, 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 utilizing two-phase system, whereas expansion valve or jetty valve can handle two-phase system. That is the main disadvantage of expansion engines. So these you can see that isenthalpic expansion for ideal gases, its value is 0. So for real gases only, this effects uh, we get, and due to that we are getting cold. So for ideal gases, you can see that Joule-Thomson coefficient is having the value 0. So for ideal gases, there won't be any change in temperature if we do the expansion using Getty valve. Real gases, say carbon dioxide, ammonia, and all other real gases, if we apply Getty valve, then there will be getting cold or cooling effect. So here it is shown that isenthalpic expansion using Getty valve. So we are getting liquid, that is the gas is initially compressed. Then in the heat exchanger, its temperature, some of the heat is taken out by this vapor which is there after JT expansion. So, with the help of that heat was taken from this incoming gas. Then this incoming gas, as its temperature is lower, then utilizing the JT valve, its temperature will be reduced, and some of the gas will be converted to liquid. So we are getting liquid and gas. This gas is returned back again. So this is that cycle utilizing J.T. valve. And another phenomenon that I mentioned, that isentropic expansion, where entropy will remain constant, and you can see that the coefficient is always positive. So we'll be always getting cooling effect by using this isentropic expansion. So this whether it is real gas or ideal gas, for all the cases we'll be getting cooling effect, and for ideal gas, its value is nu by Cp. It is always positive, and you can see that with the help of this isentropic expansion, we are getting the cooling effect directly. It is converted to liquid. So, by doing isentropic extraction, we are able to convert gas to liquid. So these are the two process by which we can get cooling effect, and we are able to liquefy. So up to this, let us stay with this, and in the next classes we will be further discussing um, in details other industrial liquefaction process, where air will be liquefied by applying various cycles. Those will be discussed later on. So that's all for today. Thank you very much.